Now for part 8. Alas, almost ready to prove the division property of exponents for irrational numbers. After some brief discussions with the intention to describe the scratch work, starting with sequence of rational numbers, because proving the said property involves taking limits of sequences of rational numbers. First, the median is the middle value in a list of numbers that has been arranged in ascending order. We have the following list, 3 through 8, then we list them in ascending order. If there's an odd number of values, the median is the single middle number, which is 8. If there's an even number of values, the median is the average of the two middle numbers. We put the list in ascending order. We have 2 through 72. The two numbers of interest are in the center of the list. They are 6 and 21, yellow box. Then we calculate the average, so add the two middle numbers, then divide by 2 to find the median. The median is 13.5, blue box. But let's try another method to find the median. The process is somewhat more tedious, but should return the results we need. Take our list from the previous blackboard. Our target number is still the blue box. We start by taking the average of 2 through 72, which returns 37. Now just replace 72 with 37 to find a new average. Now duplicate the process. Returns the number 10.5. But if we want to keep the numbers as integers, we just disregard the decimal term to get 10. Essentially, we're taking averages that approaches the target number. See that? Continue the process. Now use the new smallest number 10, add with 19 to get 14. Eventually returns the number 13. One more operation should do it. Observe, 13 plus 14 over 2 gives us the desired value, the blue box. A little tedious? Yes. But in our wake, we have two sequences of rational numbers. Both approach the target number. Take a look. We have sequence U. The first term is the greatest number, 72. The last term is the target number. All integers are rational numbers. Lastly, we have the sequence L. The first term is 2. The last term is the target number. The same can be said for these terms. All are derived from rational expressions. Next, finding the median is similar to finding the median, doing a process to find a fraction in between two fractions. But the process and the general rule is slightly different. We'll do a proof, then do an example. So the mediant inequality states, for two fractions a over b and c over d, if a is less than or equal to c over d, then the median a plus c over b plus d lies in between or is equal to the original two fractions. In notation, the white box, the general rule, the median always lies in between the two original fractions. But it's not strictly the center like the arithmetic mean. However, the median in certain cases can equal the mean. Also, the only time the median is equal to the original two fractions is when the two fractions equal each other. To save some time though, we want to prove the case where the original two fractions have a strict inequality. We want to prove the yellow box. To do that, there's two cases. For case 1, for positive integers a, b, c, and d, we have the blue box, a over b is less than the following fraction. Also, the given condition a over b is less than c over d, the orange box. In the first column, we can multiply both sides of the orange box by the product BD, which returns AD is less than BC. Next, in the second column, we find the difference of A plus C over B plus D minus A over B, which just equals the following fraction. We combined the fractions the standard way, such as finding a common denominator. Since the red box, we know the numerator is greater than 0, we know the denominator is also positive, which means the difference is greater than 0, which means the median is greater than A over B, which proves the blue box. Nice. To prove case 2, the median is less than C over D. We apply the same logic in column 1, then the difference is C over D minus the median. The said logic will follow, which means to save some time we'll skip the proof of case 2. Let's move on to another example. Then consider the irrational number square root 3, which is approximate to the following decimal number, the blue box. The first example, we essentially use the arithmetic mean to find our target number, which calculates the fraction which is strictly in the center of two fractions. But now we apply the process of the mediant inequality, the yellow box, to approach our new target number, the blue box. Similarly, we should end up with a sequence of rational numbers that approach the said irrational number. Recall the mediant always lies in between the two original fractions, but it's not strictly the center like the arithmetic mean. For example, to find the mediant in between the fractions 3 over 4 and 5 over 3, do the following. We have the middle term as 3 plus 5 over 4 plus 3, which returns 8 over 7. To start off, the first two fractions are 0 over 1 and 2 over 1, because the blue box obviously lies in between the said fractions. The first number is 1, which we'll use as our new lowest fraction to get the value 1.5, adjusting the lowest value again to get 5 over 3, or 1.6. It's a similar process as before. If we find a lower value that's closer to the target number, we use it. The same for a higher number. It looks like we're on the right track. Just 3 operations gives a sequence of fractions that are approaching square root 3. Let's continue. For example, the first fraction in the second column, 7 over 4, becomes the new highest number closer to the target, or the new C over D. The process continues. We get 12 over 7, then 19 over 11. To be clear, we've rounded the decimal numbers. Enough is enough. We're stopping the process with the last term in the third column, the rational number 71 over 41, the blue box. Take a look. Rounded off. We think the number is a good approximation of the target number. What do you think? Overall, again, we have 2 sequences that approach the blue box. One sequence, its first term is the higher value. The other sequence begins the lower value. Here, using the terms that approach from the lower value, label the following sequence S sub n, which equals, voila, we get a sequence of rational numbers that approach the target number, which is an irrational number. That's part of the plan to prove the division property for irrational exponents. We can apply the same process to target the irrational number square root 2 and label a sequence T sub n. Since the decimal part of irrational numbers is infinite, which means they don't settle down to a pattern, we can synchronize the 2 sequences, as in we can put both sequences in terms of n. For example, for S sub n, we could have began with the lowest fraction 1 over 1 and get the same result. Both sequences have 7 terms each, but take your pick out of an infinite amount of terms. Nonetheless, the target numbers will be approximations and infinite. That being said, for irrational numbers r and p, our claim for the proof, coming up shortly, is the white box. Then we know the sequences Sn and Tn are in the element of rational numbers, which means a to Sn over a to Tn just equals the following when we apply the division property for rational numbers, which we just proved in the last video. The last orange bullet, we know the expression Sn minus Tn approaches the term r minus p, which means the white box, a raised to the power of r minus p, which are irrational exponents. That's essentially the scratch work for the proof. Nice, but how does that fit in with inverse? Essentially, we did a demonstration of left and right hand side limits, which help to define continuity. We have the limit as x approaches a of f of x equals f of a. The input x could be one of our sequences that approach a equals square root 3. F of a is e to a, when the input a is applied to e to x. For continuity, The limit must exist if approached from left and right, such as our lower and upper sequences both approach the target number A. Furthermore, this common limit value must be equal to the function's value at that point, which means if e to x is continuous and injective, it's guaranteed to have an inverse.